So here we have the first one. Question number 1. X and Y are wires carrying electric current at right angle to the page P, Q, and R. P, Q, and R are the plotting compasses. Any effect of the Earth's magnetic field has been ignored. So you have the two wires, wire X and wire Y. These two wires are carrying the current perpendicular to the page. So it can be into the page and it can also be out of the page. All right, so both the options, both the directions are possible for these two. What is true about the direction and the size of the current? So direction of the current we have to answer with respect to each other. Like what is the direction of current for the X, conductor X, and what is the direction of the current in the wire Y with respect to each other, same or different? So first of all, forgetting about the size of the current, let's talk about the direction of the current. We can predict the direction of the current from the magnetic field, which in this case is being determined by the three compasses placed in the middle. So the compass P tells us that around this conductor X, the direction of magnetic field is like this one, which is counterclockwise. So that means for the wire Y, for the wire X, the current is outwards, represented by dot. Now for the wire Y, if we follow this path once again, the direction of current is once again counterclockwise, anti-clockwise. So the current would be out of the paper, because only then, according to the Fleming's right hand grip rule, your magnetic field would be counterclockwise. So the direction of current is same. We can discard option C and D. Now we are left with option A and B. Now let's talk about the size of the current. You see, the compass in the middle will tell us which one of these two wires have stronger magnetic field, and hence we can predict which one of these two wires is carrying higher amount of current. You see, the central compass is in the direction of the magnetic field of wire X, counterclockwise. So compass Q is being affected or is detecting the magnetic field of the wire X. It means X has stronger magnetic field, and conversely X would be having larger current. So we can say current in X is larger than the current in Y. So option A has to be the right answer. All right, so here we have the next one. A coil carrying current is arranged within a magnetic field. The coil experiences a force that can make it move. In which direction the coil can move? So for this one, we can simply apply the left hand rule. You see, the direction of the current on the coil, let's talk about this side of the coil only. The direction of the current is upward. Magnetic field represented by B. Magnetic field is left to right. Current represented by I is upward. And we need to find the force on that side. Force represented by F. The direction is question mark. Now we can find the direction by stretching the three fingers of our left hand in such a way they are perpendicular to each other, and in this case the direction of force on the left side of the coil appears to be inwards. On this side the force appears to be inwards. Alright, so your forefinger was towards the left side, so sorry, your forefinger was towards the right side, current was upward, and the thumb points into the paper, so the force would be inward. So the direction in which the coil move, it cannot move along the direction of magnetic field, cannot move from X to Y, cannot move out of the paper, it turns about the XY axis. So D has to be the right answer for this one. Your coil would start spinning or turning around this axis. So this is a line around which your coil turns, and it would turn in this direction like this. Moving on to the next one, question number 3. This is from the topic of loudspeaker. We study that in detail. The diagram shows part of the loudspeaker. Which type of current is passed through the coil and why? First of all, we always use AC current, alternating current, I should say AC signal or alternating current for the loudspeaker. So option C and option D are thrown out the window. And the reason is we use the alternating current, so in first half cycle the coil might be moving forward, and in the next half cycle the force would change the direction and the coil might the cone might be moving backward. So in order to have the forward and backward motion, in order to have the vibratory motion, we need to have the alternating current. Only then we can produce the sound waves. So B is the right answer for this one, to make the coil vibrate. Two parallel wires carry currents in the same direction. Which part shows the magnetic field around each wire and the direction of force on each wire? First of all, this is from the topic of force between two parallel current carrying conductors. And from that topic, the final verdict was, if you have like conductors, they attract. And if you have unlike conductors, they repel. Unlike conductor means with respect to current. If current is in the same direction, the two conductors would attract each other. And if the current is in the opposite direction, the two conductors would appear to repel each other. So in all the four options, or over here in the very first sentence, they have mentioned this thing, that the current is in the same direction. So there has to be the force of attraction. You need to get rid of the option C and option D, because these two options state that the force is repulsive, because the conductors are moving away from each other through the middle. But if the current is in the same direction, the force should be attractive, and it has to be between A and B. And if we apply the if we apply the right hand grip rule and the current is downward, the magnetic field would be clockwise. So this one is clockwise, this one is clockwise, this one is clockwise, but here we have a problem. It is counterclockwise. It should have been clockwise, so B is also discarded. We are left with the option A, which is the right answer. A current in the solenoid creates a magnetic field, and also you need to see the pattern of the magnetic field. They ask you for 2 marks, sometimes 3 marks, to draw the pattern of magnetic field for the solenoid. If they have given you in the middle, they have given the iron core over which they have wrapped, over which they have wounded the coil. So you don't have to draw the magnetic field lines in the center. You just need to start the lines from here. Extend the lines like this. If the central part of the solenoid is wounded on a core, iron core. But for this situation, since there is no conductor, there is no metal in the middle, they have represented all the magnetic field lines. In the central region, the magnetic field is treated as uniform magnetic field. Anyway, the question is, what is the effect of magnetic field at the point P? I mean, at this point, using larger current and in the opposite direction. Well, obviously, the magnetic field is there due to the current. So if you increase the value of current, the magnetic field should have been increased. That's pretty much common sense. If the magnetic field is due to the consequence of current, then you reduce the current to 0, magnetic field vanishes. You increase the current, magnetic field gets stronger. So A and B discarded. It has to be between C and D. And if you reverse the direction of current, the direction of magnetic field also reverses. So it is the C. So if the direction of magnetic field, direction of current is reversed, let's say this is the new direction, then this one would become the north pole and this one would become the south pole. All right, once again, we apply the right hand grip rule in order to find the direction of the magnetic field for the solenoid. Screening of the metals used to be in the syllabus, but now they have discarded. Alright, so here we have the next one, question number 7. A copper wire is held between poles of a magnet. The current in the wire can be reversed. The poles of the magnet can be changed over. In how many of the 4 directions shown can the force act on the wire? The answer for this one is 2. And matter of fact, this is a question from the workbook, and I explained over there in detail that the force can act only in 2 possible directions. Let's say the magnetic field is from left to right. Now, left to right or right to left, both of the directions are being occupied by the magnetic field. So the force cannot be in either of that direction. And the force cannot be in the direction of current or opposite to the direction of current. The force has to be perpendicular not only to magnetic field but also to current. And there you're left with only 2 possible directions. So if your magnetic field, let's say magnetic field and current here, then you have force. If the magnetic field is, let's say, towards the right side, current is upward. So your right side, left side occupied, current was upward, downward occupied. The only 2 options for the force would be outward or inward. This is how it works. The diagram shows a coil in a magnetic field. When the coil is a part of the DC motor, what must be connected directly to the X and Y? Okay. what must be connected directly to the X and Y? So we have this thing. First we take the split ring commutators in order to make the coil move in a single direction. Then we have the carbon brushes, then we have the contacts, then we have the battery, then we can have the variable resistor to control the battery. We can also have the switch, stuff like that. But the part that is directly connected to X and Y is split ring commutator. So for this one, D is the right answer. The diagram shows forces F between two wires carrying currents out of the paper. The magnetic field lines close to the wires are also shown. Which of the diagram is correct? All of them, current in all of them are represented by a dot. And dot represent that the current is out of the paper. So the two wires are carrying like current. Like current means in the same direction. In this wire current is outward, this wire current is outward. So this pair has like current in the same direction. And if we have like current, then the two conductors should be attracting each other, because this is what we study in the theory as well. So A and C discarded because the conductors have to be pushed towards each other, but A and C shows the conductors are moving away from each other. So it has to be between B and D. Now we will find out the direction of the magnetic field if the current is outward. If the current is outward, the direction of magnetic field is counterclockwise, right? According to the right hand grip rule, your thumb should be pointing towards you and your fingers would curl in this way, right? If your thumb is pointing towards you, your fingers would curl counterclockwise. So D is also discarded because there's an inconsistency here. So B is the right answer. Alright, here we have the next one. In a DC motor, the coil is wound on a soft iron cylinder. Why is a soft iron cylinder used? We use it for this with the solenoid to increase the strength of the magnetic field. So this is a fact based. We also study that in theory, that if you insert an iron bar inside a solenoid, the magnetic field strength of the solenoid would increase. So here we have the next one. The diagram shows a beam of electrons entering a magnetic field. The direction of field is into the page. So I can draw the direction of field into the page. That would look something like this. The magnetic field is into the page. In which direction the electrons are deflected? Now for this one, I've explained that once you're having a charged, negatively charged particle, then you can apply the same rule, the left hand rule, but with your right hand. Or if you don't want to apply with the right hand, you want to go with the left hand, then your middle finger has to be in the direction opposite to the direction of the electron beam. So if the electron beam is moving forward towards the right side, your middle finger or the second finger has to be towards left side. So this should be the direction of the second finger. because the concept is, because according to the Fleming's left hand rule, the middle finger represents the direction of current. The direction of current is conventionally from positive towards the negative. The electron beam moves from the negative towards the positive. So in order to make it consistent with the conventional direction of the current, we move the middle finger in the opposite direction. But if you apply with the right hand, then your middle finger has to be in the same direction as the electron beam. So this one is for the left hand. Your forefinger or the first finger would be inward into the page, and your second finger would be towards the left side, and you can find the direction of force. So if I apply the left hand rule on that, so middle forefinger was inward, and the direction of force comes out to be downward, that is towards the bottom of the page. Yeah, towards the bottom of the page. And when I applied the left hand rule in such a way, my forefinger was inward. I put my forefinger exactly on the sheet of paper. My middle finger was towards the left side, and my thumb was then thereby pointing downward. And once you're applying the left hand rule, I mean, that's a very common mistake. I tell you repeatedly, you're not allowed to move your fingers. Just stretch your fingers once and for all, and after that, all you have to do is either to move your wrist or to move your elbow, to rotate your arm, or to rotate your hand. But don't keep moving your fingers. Alright, then we have the next one. Which single motor will have the largest turning effect? So motor is based on, once again, it as an input, it takes the electric current. So the more the current, the more would be the force on each side of the conductor of the coil, on either side of the coil, and the larger would be the turning effect. So if we have more current, there would be more force, and if we use an iron core in the middle, there would be larger turning effect of force, because there would be stronger magnetic field, and due to stronger magnetic field there would be stronger force. So first of all, we can discard A and B because they tell us without using the iron core. So it has to be between C and D, and we'll go with D because in the option D, we not only using the larger current, but we also using more number of turns. And the more number of turns, the more current, the more magnetic field, the more is the turning effect of force. In the circuit shown, all lamps are identical and all cells are identical. The resistance of the coil in the reed switch is negligible. One cell lights one lamp to normal brightness. Okay, what is the brightness of the lamp when the switch Y is closed? So if you have closed the switch Y like this, so previously what was happening previously is, first of all, lamp P was not operational previously. Now as the current flows through it and this switch is closed, the switch is now closed like this, the current flows through the lamp P and the lamp P operates to the normal brightness. So P has to be first of all to the normal brightness. You can discard A and D. So it has to be between B and C. Now C says that this lamp Q and the lamp R would be turned off. Now the thing is, as the current flows to this one, through the first one, through the lamp P, as the current flows through this one, the magnetic field produced in this portion would make the contacts of the reed so it join, and the above circuit would also be completed. But since one battery was able to lighten up only one bulb properly, but here in the upper circuit we have two light bulbs which are connected by one battery, so the light bulbs would turn on but they would be dim. So we'll be left with the option B. Alright, then we have the next one. The diagram shows a simple electric motor. The split ring commutator reverses the direction of the current in the coil as the coil rotates. The coil is rotated 360 from the position shown. How many times is the current in the coil reversed during full range of motion during 360 degrees? In the working of the split ring commutator, this is a point that we write explicitly, that the direction of current is reversed twice in 360 degrees. It would be first reversed when the coil reaches the vertical position, and it would be reversed when it reaches the other direction, when it gets back to the original direction. So it would be reversed twice. Then we have question number 15. In each of the diagram is a cross section through two parallel current conductors. Which diagram shows correctly the magnetic field pattern and the direction of forces on the two conductors? So once again, I explain it this way. If you have like conductors, their shape will look like the Xbox controller. And if you have unlike, it'll be looking like this thing. You can call it eyes or whatever. And for the like conductors, not only they look like Xbox controller, the force would be attractive. They would attract each other, and in this case they would repel each other. So this one is unlike. All right, current is inward, here it is outward, and the force for the unlike has to be repulsive, but this one says attractive. For the option B, once again, these are unlike conductors. The current is inward, the current here is outward, the force has to be repulsive. This one also discarded. Then we have C. C says unlike. Okay, the force has to be repulsive. It is repulsive. And for D, we have unlike, and unlike repel. They repel, but they don't look like, once again, they don't look like the Xbox controller like this. This is only for the like conductors. So C is the thing that checks, for which we can check all these three boxes. They do look like the direction of the magnetic field or the magnetic field pattern. Overall, it looks like the eyes pattern. They repel each other. There's a magnetic field line in the center. It checks all the boxes. An AC is applied. Alternating current supply is connected to a wire stretched between the poles of a magnet. Which way will the wire move? So the direction of current is this one. You can say either inward or outward. Because since this is alternating current, the direction of current would keep changing periodically. So it would either be inward and outward. The direction of magnetic field is left to right. So you have 6 options for all the directions, right? You only have 6 options: up, down, left, right, and the last one, in and outward, inward and outward. So left and right, this direction is already occupied by magnetic field. Magnetic field is from left to right, but the force cannot be parallel to magnetic field, so we say the left and right, both directions are occupied by the magnetic field. In and out directions are occupied by the current. So we are left with only up and down. So the force can only be upward or downward, but in this situation the force would be in half cycle, it would be upward. In the next half cycle, it would be downward. All right, so here we have question number 17. A DC motor consists of a coil of many turns rotating in a fixed magnetic field. The coil is connected to a DC supply through a split ring commutator. Okay, some changes are made one at a time. The DC supply is reversed. The coil, okay, for these changes are made, let me read the question first. How many of these changes will make the coil rotate in the opposite direction? Okay, if you reverse the DC supply, the coil would move or rotate in the opposite direction. The coil is turned before switching on so that P starts on the right and Q starts on the left. No, that doesn't do anything. The poles of the magnet are reversed. Yes. The turns on the coil are increased in number. No. This only changes the magnitude of the turning effect of force. So how many of these changes make the coil rotate in the opposite direction? Only 2. Reversing the supply and reversing the poles of the magnet. And matter of fact, if you do both of them together, the direction of force would once again not be reversed. It would be what it was previously. Alright, which diagram shows the direction of the forces acting on the 2 conductors? The force acting on the 2 conductors is not sideways, so A and B are discarded. It is always towards, it is always attractive or repulsive. And if you have unlike conductors, the force is repulsive. If you have like conductors, the force is attractive. So these are unlike conductors. The force cannot be attractive. It would rather be repulsive. A simple model of a DC motor is made by mistake. The split ring commutator is left out. The coil can turn but is always connected to the battery in the same way. The coil starts in the horizontal position. What happens to the coil when the circuit is switched on? Well, the thing is, it will reach uh, to the vertical position, but then the direction of force acting on this side would once again be reversed. So first, if the force was upward, next time the force would be downward, so it would keep oscillating. So it does not move at all, no. It moves upward out of the field, no. It turns to the vertical position and eventually stops there, no. It turns to the vertical position, then comes back to the horizontal position. So it would not be moving in a single direction. It would keep switching the direction of rotation. So D is the right answer for this one. A long flexible wire is wrapped around two wooden pegs. A large current is passed in the direction shown. Which two pairs of length of the wire attract each other? The portions which have the current in the same direction would attract, and those two are J, K, they would attract each other, and L and M would attract each other. So J, K and L, M. Like currents attract. Alright, once again, the thing is, it's not the current that is attracting or repelling, it's the magnetic field that is produced due to the consequence of the current, and the magnetic field for the like current adds up in such a way that the magnetic field in the middle becomes weak, and at the sides the magnetic field is strong for the like conductors, for the like current, and due to which the conductors move from stronger magnetic field towards weak magnetic field. Now this is something that we study in theory in detail. The diagram shows a DC motor. Why is the split ring commutator used? Okay. Alright, so this is what we study in the definition of split ring commutator: to change the direction of the DC supply as the coil passes the vertical position. Then they would change the direction of the DC supply. So this is why we use the commutators. So as soon as the coil has moved to this position, after that they'll just change the direction of the current on both sides. The diagram shows a beam of electrons entering a magnetic field. The direction of the magnetic field is downward towards the bottom of the page. The electron is moving towards the left side. In which direction does the deflection of the electron occur? So your forefinger for the left hand, if you're applying the left hand rule, your first finger or forefinger has to be towards the right side. Forefinger, not force. Forefinger has to be towards the right side because the electrons are moving to the left side, but the direction of current is from positive towards the negative, so it would be towards the right side. Magnetic field is downward. Sorry, not forefinger, the middle finger has to be towards the right. Middle forefinger in the direction of magnetic field, which is downward. So middle finger on the right side, forefinger downward. And if I apply the left hand rule in that situation, the current comes out to be, the force appears to be inward. Your thumb points inward into the page. What does not alter the size of the turning effect on the coil of the electric motor? The direction of the coil in the number of turns, it does change. The size of the current in the conductor, it does change. The turning effect, the magnitude of the turning effect, the strength of the magnetic field, you increase the strength of the magnetic field, the size of the turning effect does increase. The only thing that does not change the size of the turning effect is the direction of the current. If you change the direction of the current, the thing that changes is the direction of rotation. So it would be the direction of the turning effect that is changed due to the change in current, not the size. Alright, so this one would be the last one for today. The diagram shows an alarm system in which the switch S is closed. Switch S is shown closed. Okay, so switch S is closed. Okay, what happens when the switch S is open? So remove from here, and now the switch S is opened like this. So what happens now? If the switch is open, previously when the switch was closed, the current was flowing through here. Iron core was magnetized. It had attracted this iron strip upward. It had pulled the iron strip upward, and the circuit containing the bell was incomplete, and the bell would not rung in this position. Now if this thing happens, what is going to happen is, next is the iron bar, since it is not magnetized, the iron core is not magnetized, it would no longer be attracting the iron core. The iron core would drop over here. These contacts would join. The circuit is now completed. The bell current would flow to the circuit and the bell would ring. So iron drops and the bell rings. So A is the right answer for this one.